Hello and welcome to the fourth lecture of my operating system development lecture series. Today I'll be talking about going into protected mode, and for that I will be talking about how to set up a global descriptor table. I'll be talking about the A20 line, and then I'll actually talk about how to get to the protected mode. So let's begin. First, I would like to address, a little pun, the A20 line, which is the sort of relic of the past. So, as I have previously mentioned, in real mode, there is a usage of the 20-bit addressing system, right? So we have the segment, we have the offset. So back in the days when you just had 16-bit x86 CPUs, they would all have, or at least a majority would have a 20-bit address bus. So, because of that, right, all of the different programs and their memory allocation and everything, it was made with a 20-bit address bus in mind. So then, eventually, people have started making 32-bit CPUs, right? But porting software was very difficult. Now, not only did people have to change the instruction structure and such to match new 32-bit CPUs, one problem was that people were considering a 32-bit address bus. Right, it seemed like a quite logical step when creating a 32-bit CPU. However, that was quite problematic because that would just add an extra step of complexity if it comes to porting 16-bit software. That is because this old software was designed for taking advantage of the 20-bit bus. And it was only designed for dealing with this address space. Then if you tried to implement things that would use higher addressing, you know, the other algorithms which did not predict that would not deal with that and would therefore have to be changed. To prevent this, they invented a sort of, you could even call it lazy solution, because many people do like to critique it. It is called the A20 line. So A in A20 stands for address, right? So it's the address line 20. So basically, what they said is, okay, we will literally restrict the amount of the address bus that can be used to 20 bits. So this is a solution, and it was a relatively good solution at the time because programs did not require that much memory, and it was just easier to port 16-bit software. So it was a relatively good solution, but it has okay. So it is some sort of solution to this problem, and so you would have this feature of the A20 line, which would allow you to go further, right? I'm not sure if I phrased that correctly. So you had a restriction to 20 bits of the address bus. By default, all programs would only be able to access 20 bits of the address bus. If someone, for some reason, you know, if they needed more memory, if they needed something more advanced, if they needed 32-bit addressing, they could enable the A20 line and thus have access to the rest of the bits of the address bus, the rest of the lines, the lanes, and whatever you want to call them, channels even. Right, so that's the idea of the 820 line, and then when new processors were made, you know, we were like, okay, you know, since this was like disabled by default, you know, let's, for compatibility purposes and stuff, you know, let's just keep it disabled by default. And basically for this very long time, you know, it was just like, okay, backwards compatibility, and it eventually became the standard. And it is normal right now that pretty much every x86 processor has the 820 line disabled by default. So this is the sort of relic of the past, sort of annoying even, where we have to enable the 820 line to be able to actually address more than 20 bits. Or we can use more than 20 bits to address. I think that's a better way to word it. So sadly, this didn't evolve into new processors that it should be enabled. But what has evolved is the way that the 820 line can be enabled. So what is very convenient, highly convenient to programmers nowadays, is that there is a feature on most CPUs that is called Fast 820. And Fast 820 is a feature that, so you could even just call it a bit, because basically what CPU manufacturers have done is they've simplified the whole act of enabling the 820 line to flipping a single bit. So this feature, it's called Fast 820, right? You simply have to read from a port. The port number in hexadecimal is 92. So you have to read from that port. You have to flip the 820 bit and then write to that port. That's it. And this is supported by most x86 CPUs nowadays. This is Fast 820. It's this extremely simple way to turn on the 820 line. To enable it, you can simply set this bit to 1. So in order to read from this port, right, you would use an x86 instruction, just such a, obviously this is an I/O port, by the way. You have to communicate through the CPU's I/O bus. So what you're going to do is just in, and by the way, this is an 8-bit value that you're going to read. This is an 8-bit value that is stored in this port. So we're just going to use an 8-bit register, like the lower A register, but you could use any other 8-bit register that is to your liking. And you simply get the value from this port using the I/O bus. Then you have to flip the bit, and the bit that is responsible for this is the second youngest bit. So the second youngest bit. So if we think about representing it as a byte, right? We have some values. We have 6 bits. Then we want a 1, no matter what. And then we don't really care. So how can we ensure with a logical operation that we will end up with a value of this form? Well, we could simply perform an OR operation, right, which can flip this so the second youngest bit to a 1, right? So we can simply store the value 0, 0, 0, 0, 0, 0, 1, 0. And then, when you OR the value that you read from this port with this byte, you can be entirely sure that the result will have a 1 in this place. And this means that the fast A20 bit is going to be 1, and hence the A20 line is going to be enabled, as long as fast A20 is obviously supported. We can actually simplify this a little bit in our code from a practical perspective by noticing that this value is simply of a byte for the number 2 in decimal. So we can OR our value of AL with the number 2. And this will flip the fast A20 bit. Now, you might be thinking to yourself, if you're already sort of experienced with flipping bits from different registers and such, from different ports, you might be asking yourself, well, why don't we use XOR, right? Why don't we use an exclusive OR? Because an exclusive OR is actually what flips a bit, right? Because when you have some value, right, and you XOR it with 1, right, then if you have some value, right, you have some value, if you, and you have some value, you XOR it with 1, then if it was 1, then you're going to get 0, so you flipped the 1 to a 0. If it was a 0, then it's going to end up being a 1 from the XOR. So an XOR operation is what really does this. Also, we can't use NOT because NOT takes a single parameter. I would just like to mention that. Yeah. So why don't we use the exclusive OR gate? And the answer is simple, because we don't actually want to flip the bit. That is because on some CPUs, that is very rare, but it can happen, if they can support fast A20 and the A20 line can be enabled by default. This is very rare, but for compatibility purposes, it's good not to flip this, but just ensure that this bit is going to be equal to 1. Because this is our goal. Our goal is to make this bit 1. To make sure that fast A20 is enabled. We don't want to flip it. We will usually flip it because the bit will be 0 because the A20 line is usually disabled. But it can be the case that that it is enabled, and in that case we don't want to flip it to a 0, we want to keep it as a 1, and in this case the OR gate, when it's going to take a 1 and a 1, it's still going to return a 1, unlike an exclusive OR gate. Which is why we use this OR operation over here. Then we want to write to this port, which we do through the CPU's I/O bus again. So we simply perform an out to the ports with our new value that we performed those operations on, which in my little example was stored in the lower A register. Again, you could have used the higher A register, you could have used the lower B register, it doesn't matter. We're just trying to store this 8-bit value from this hardware port, and we simply out our register that we performed this OR operation on back to this port. And just like that, you've enabled the A20 line on most CPUs. And this is very useful, because now when we will go into 32-bit protected mode, we will be able to address more than just 20 bits. So we'll be in a 32-bit CPU mode, and we'll actually be able to use 32-bit addressing. So that is a very important consideration that one should probably execute at any point before going into protected mode. So I just wanted to mention this A20 line. Right, so now the slightly more difficult part is the global descriptor table. So the global descriptor table is a pretty valuable lesson because it sort of teaches you how to follow a format and just give values to a format and then load it by some means. So this is a simple, very simple exercise that can always help. But what even is the global descriptor table? What is it for? So the global descriptor table, or the GDT, as the name suggests, it's a table. So it is a collection of different values. Now this table is global, which means that this table will be accessible to us anywhere in our operating system. Then you have the descriptor part, and a descriptor, as one might guess, is something that describes something. So we have a table of descriptors, which are values that describe something. To be precise, this global descriptor table contains information about different segments in memory. So we have those different segments, and we need to say, we need to specify things like, okay, what is the base address? So at what point can you find that the earliest? What is the limit address? So beyond which point can you not find that thing? How can you access that thing? How should that thing be addressed? So on. And this is actually a very vital component of the very idea of protected mode. Because the protected mode, as the name suggests, is just a protected mode of the CPU. Many people mistakenly think of it as the 32-bit CPU mode in x86. This isn't the entire picture. And that is because when you're dealing with 32-bit code, it might not be protected, because you could as well be in something like Unreal mode. That exists. Perhaps it's not that common, but it exists. And there's also 16-bit protected mode, which is a protected mode as it offers protection features, but it is not 32-bit. It is 16-bit. So I would just like to point that out. The name protected mode is there for a reason. It actually protects something. And the global descriptor table is a pretty vital part of it, because it is one of it can be used for triggering something called the GPF. So a GPF, it's short for a general protection fault, and those are faults which are caused when, for example, some memory is not accessed in the way that it should be, or some code that shouldn't be executed is executed. So this is a vital protection feature, this general protection fault. And the way that a CPU usually manages GPFs so well and triggers them is through the global descriptor table. And this will, for example, allow you to later, even when you're making user space applications, you'll get general protection faults when you will try to do things that are not allowed. So I will be talking a bit more about that later in this lecture, but when these user space programs do things that shouldn't be done by user space programs, it will also trigger a GPF. So the global descriptor table is really an important component of protected mode, and it is required for going into protected mode. Right, so what are the actual parts of GDT? And I'm going to be completely honest here. I don't remember everything about the GDT because I usually just look at a CPU manual. I remember most of it. I might even remember all of it. It might just have, it might have just happened, but I do remember all of it. But just in case, I literally have a piece of paper right next to me that I might take a look at if I ever forget something about the GDT during this lecture. So people don't usually memorize the whole GDT. Anyway, what is a global descriptor table comprised of? Well, usually there's first something called the null descriptor. Then you have your code and data descriptors. Then you have the GDTR, which is the global descriptor table register. And I should have actually written this here, but let's just say, yeah, just actually erase that. So you can have a task state segment descriptor. This is TSS for short, and then you have your GDTR. Okay, so what are those? So if it comes to the null descriptor, it is literally 8 bytes of just zeros. It's 64 bits of zeros placed next to each other. So this might seem a little strange, but it's actually very important because it allows you to, the CPU to nullify descriptors when it is necessary and to properly deal with the GPFs that I previously talked about. So for the programmer, not really an issue, but it's pretty important for the CPU. Then you have the code and data descriptors. So a code descriptor, I think it's pretty self-explanatory. It is it's 8 bytes that describe the details that I previously talked about, segments like the base address, the limit address. I'm going to write that down as well soon. It specifies all of that about the code, the actual executable data. Well, I shouldn't say data, the executable ones and zeros. So, as you might know, code and data are not really, you can't really differentiate between them on a low level, because code is a sequence of ones and zeros. You know, it corresponds to opcodes, to operands that your CPU can fetch, then decode and execute. And generally, you know, data is also just ones and zeros, except it can represent some value, or it can represent a type of something, right? So fundamentally, they're the same thing. We as humans see them as something different. And in order to sort of formalize this distinction a bit more, and for the CPU to know what is code, what is data, how to differentiate between them. You have to load a GDT with code and data descriptors. So that's what they're for. And yeah, the descriptors themselves, they allow you to say, for example, how the data should be accessed, how the code can be accessed. I'm going to go into details later. So those are the code and data descriptors. Then you have the task state segment descriptors. Now those are actually optional. Those are optional. And a task state segment, it is usually used when you actually when you make user space multitasking. So I'm going to be talking about multitasking in a lecture that will come probably in like half a year or something, considering my tempo. I'll try to speed it up a little bit, don't worry, but to give you the bare idea of multitasking, right? You start executing a task, and then when you want to execute another task, right? Because multitasking, right? A CPU can only execute one instruction at a time. So a common misconception is that when you run multiple programs on your computer, all of them are actually running simultaneously, as in your CPU is doing an instruction for your browser, for your video game, for your instant messenger program, whatever. This isn't actually the case, because yes, there is multi-core, right, which is, you know, having multiple CPUs really, and them having execute instructions independent of each other and use symmetric multiprocessing, SMP and stuff, right? But the essential idea, right, and the way that multitasking machines existed on single core CPUs is because they have something called a scheduler, which wisely gives CPU time to different processes. So you have some process running, right? And let's say it's your browser, and then you also have some video game, and they're supposedly running simultaneously. But what actually happens is it starts executing browser code, and then when the scheduler decides that now the video game deserves some time, if it comes to this time, we're talking nanoseconds. So, and when it starts executing the video game code, you know, it has to ensure that when it goes back to the browser, it is in the same state that it was. And for that, you use a mechanism called a context switch, where basically what you do is you store something called a context, which is basically the state of the process. So you have a bunch of browser code that executes, and then once it's time to go to the video game code, it does a preemption, and it saves this state that the browser was in, which is called this context. So it has this context stored in memory, and then it starts executing the video game code. And once it's done with the video game code, it places the state of the video game into the memory. Again, this is called a context. And then, and the reason this is called context switching is then when you want to execute browser code again, it switches this context to what the browser had saved in memory. So now it takes the browser's context, and now the browser knows where it left off, and it can execute code from the point that it ended, with all the register values and such that it had at this point. And then once it's done, it loads the context for the video game, and then the video game can execute code from the same state as it ended in. So this was, again, you don't have to understand all of this because I'm going to go in depth and in a later video, but to explain what a task state segment is, it's basically that context. Well, this is a descriptor for them, for TSS, but every task in at least in proper user space multitasking, how it should be, should have a different TSS or a task state segment that describes this the state of a process or the context, right? So this is the TSSD or the task state segment descriptor. Those are optional because obviously when you're still running in rank 0, I will talk about that in this lecture. But for now, you know, we're running in not user space. Let's just put it like that for now. We obviously aren't forced to create task state segments because we're not going to create user space multitasking at the moment. Then you have the GDTR. So this is simply a descriptor. You could basically call it a descriptor. It's a bunch of information about where the GDT starts and how long is the GDT. That's pretty much the only two things that it specifies. Where's the GDT and how long is it? So obviously where it starts, that is pretty obvious. We obviously want to know where our GDT begins. As for the size, it is also useful because the size of a GDT is not fixed. The reason for that is because, for one, you know, you have optional task state segment descriptors. So, you know, just because of that, the GDT is going to vary in size. Generally, if you'll want to implement user space, you probably don't want to use the same code and data descriptors that you use for your kernel. So you have to also create a user space code descriptor and a user space data descriptor. So the size of the GDT can vary. Okay, so now we have a general idea of how the GDT is built. And we can just ignore this for now. And you will simply just place these three, preferably just next to each other in memory. Actually, I'm pretty sure it has to be next to each other. I'm actually not sure. I think the GDTR can be separated, but these components, and if you had TSS segments, they have to be together. Because the CPU instruction is going to read them like so. Anyway, but preferably just place the GDTR and just write afterwards as well. And we're going to talk a little bit about the structures of those. So the first is the null descriptor, which I have pretty much entirely described. And in fact, I can write 4 characters, or for me, since this whiteboard is, as the name suggests, white, I only have to write 3 characters, but on a computer it's 4 characters. DQ 0. I think this is a whole null descriptor. So a null descriptor, again, it's just 64 zeros. So this is literally the null descriptor. This is literally the whole piece of assembly code that is a null descriptor, because it defines a keyword, which I'm pretty sure is 64 bits, right? Because you have a word and double word. Yeah, but so that's a quadruple word, a keyword. So that's 64 bits. This is your whole null descriptor from a practical perspective. So, well, that was easy. let's now talk about the code and data descriptors. Their structure is very similar, so I will just talk about a general segment descriptor, and this is going to apply to both code and data. So before we properly place it into the GDT format, which I'm going to talk about, let's first even list the parameters that we can set and ponder about to what value should we set those parameters. So the first thing that we have to specify is the base address. So this address is what is the earliest memory address that you can find this thing at. So it will trigger GPF if it finds if it tries to access that thing as that thing before that address. So for example, if it tries to access a bunch of ones and zeros as code, where the code descriptor says that there shouldn't be code there. So this is the base address, the earliest address. Then you have the limit address, which dictates the maximum address for that thing. So it's the opposite of base address. Then you have to specify access permissions, which I'm going to elaborate on. And then you have to also specify flags. Okay, so let's now think about what we can set all of these things to. Let's first think about the base address. Well, for our purposes, we could just set the base. Also, I should probably mention the base address is stored as a 32-bit value, and the limit address is stored as a 20-bit value. Again, this is a relic of the A20 line and the 20-bit address bus for real-mode CPUs. And when I'll talk about flags, I'll talk about how to ensure that we aren't limited to this 20-bit addressing when specifying the limit address. But for now, let's think about the base address. Well, for our purposes, we can just set it to 0. We could set it to the lowest possible address. We don't really care. We could just say that code can be anywhere, data can be anywhere. We can use our whole memory for anything we want. So this might be changed, especially should be changed when you go to user space and you should dictate what is going to belong as kernel code and user space code. But for now, we could literally say we want this to be 32 zeros, which I guess would be 0x000. No, that is so it has to be 8 hexadecimal zeros. I'm just going to write it in hexadecimal so that it's shorter. 8 hexadecimal zeros, I think that's 32 bits. Then you have to specify the limit address, and again, using the same logic, let's just use our whole memory. Let's say code can be anywhere, data can be anywhere. So since this is a 20-bit value, right, we can make this 0x f, 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 f. So the maximum 20-bit value written in hexadecimal for simplicity. Okay, so now we have specified 2 of the parameters that we have to specify for a segment in our segment descriptor, the base and the limit address. Now what about access? So the access is really just a single byte, where every bit or collection of bits actually corresponds to some given access parameter. So the first one is the present bit. And the present bit, it always has to be set to 1, because it dictates whether something is even a valid segment. this could be set sometimes to 0 as test and like segment test, but generally you'll want this to be 1 because you obviously want your segment to even exist, to be present. So the present bit is going to be 1. Then you have 2 bits to specify the DPL, which stands for desired privilege level. So for that I have to talk a bit about x86 ring protection. So I don't actually know how people do the diagram, but I don't think I actually need a diagram. Should I do a diagram? Whatever. Let's do a diagram. So x86 offers something called the ring protection, or a ring system. The idea is that you have those rings which get smaller and they correspond to the amount of instructions that you can do, or well, not really just instructions, or rather permissions that you have. So what instructions you can use and how you can use some instructions if it's risky. They're just a protection feature where you consider ring 0, the most outer ring, to have basically, well, not unlimited, but a lot of permissions, the most that x86 gives you. So ring 0 is really this pure raw mode where you can pretty much do whatever you want. You can communicate with an ATA driver and wipe out your whole hard drive if you want to. Yeah, so that's ring 0. Ring 0 is the maximum amount of permissions. And ring 0 is also called the kernel ring. And that is because that is the ring that your kernel should run in, that pretty much has to run in. So ring 0 is also called the kernel ring, with the maximum permissions. Now I'd like to talk about the very opposite, ring 3. Ring 3 is a ring with very minimal permissions. It can do a very low amount of things. And ring 3 is usually just called the user space. And the reason for that is because user space code should be executed in ring 3, because the user should, by design, have minimal permissions. So in most operating systems, your user space is going to be running in ring 3, as you don't want the user to actually have the same amount of access to hardware as your kernel does. There's also ring 1 and ring 2. And they're sort of in between. They have some permissions that ring 0 has, but you know, not all of them. So ring 1 and ring 2, they're usually used for drivers. So ring 1 and 2 are usually the driver rings. And that is because, you know, a driver, it often shouldn't have kernel permissions, right? You think of drivers as those intermediates between hardware that you use and the user, that dictates how this device should be properly managed. And you know, they shouldn't just run as normal user space programs, which is ring 3. They shouldn't have such minimal permissions. They also probably shouldn't have kernel permissions, which is why ring 1 and 2 are usually used for drivers. Ring 1 can also be used for system calls. For various designs, you can use them as you please. But this is the general structure and have their general use. Sometimes ring 1 and 2 are not used. They're not used for drivers. Drivers run in the kernel. You can run drivers as kernel modules. You can have a modular kernel. That is called a monolithic kernel, right? Where you put everything into the kernel. I talked about that in the first video. So usually when you have monolithic kernels, so you put everything into the kernel or drivers and such, it's going to be all running in ring 0. So that is the ring protection system. And rings are also often more formally referenced as privilege levels, which makes sense because that's what they fundamentally are. So this is our desired privilege level, and you'll actually see these acronyms very often in the OSDev. DPL stands for desired privilege level. CPL, that you'll often see in debug logs and such, stands for current privilege level. So, okay, some code was executed, and what privilege level was it executed? That's your CPL value. And the desired privilege level is this theoretical value of what do we want to, what privileges do we want this to have. So, if it comes to the desired privilege level, you simply put the ring number in binary, right? So ring 0 would be 0, 0, ring 1 is 0, 1, ring 2 is 1, 0, and then ring 3 is 1, 1. I hope that really should be clear. So if it comes to the DPL, I would just recommend setting this to 0, 0. Because, well, we're currently writing a bootloader, or at least I'm talking about the theory behind a bootloader. You obviously don't have to write it, you can use Lemonade. Since, you know, this is a bootloader, and we're doing a lot of hardware stuff, we should have hardware permissions. And then we're going to be loading a kernel. The kernel, as I said, should run in ring 0 and should have maximum permissions. So the desired privilege level is going to be 0, 0. Then, I think the next one is segment type, but I'd just like to verify that. Yes. So this is a segment type, or S, and this bit simply dictates whether this is a TSS or not. So is this a TSS or is this a code or data descriptor? If it's a TSS, then we set it to 0. If it's a code or data descriptor, then we set it to 1. And since we're currently not trying to make a TSS descriptor, then we will simply set this to 1. Then the next bit is the executable bit. And the executable bit, as the name suggests, tells us whether the segment is executable or not. This is just a very cryptic way to say, hey, is this a code or data descriptor? Because obviously the only descriptors you have here, except for the TSS descriptor, is either code or data. And code is executable, data is not. So this is pretty much the distinction between them. And the executable, right, is going to be 0 or 1, depending on whether you're currently making the code or data descriptor. Okay, then we have a direct/conforming bit. And I think that this bit is first, and then you have the read-write. I'm going to check that. Yes, okay. So this is the direction / conforming bit. So when you're in a data descriptor, so if this is 0, right? So now the CPU knows that you're describing a data descriptor. It's going to be the direction bit. So this is going to simply state whether you want to, when you have data, does it go from the base? So does it go from bottom to top, or does it go from top to bottom? If it comes to addressing, so you could just set it to 0 for the code segment, which just means that it goes from bottom to top, or you could have it the other way around with 1. It really doesn't matter that much. I mean, it matters when you look at your memory structure and such. Yeah. Yeah, and the other bit is the conforming bit, which this is the one that you will have in code descriptors, and it's the bit that dictates, okay, can this code that is placed in these bounds, can it be executed in the privilege levels that are below the DPL that is specified. So this means that, for example, if we were making a user space code descriptor and we set the DPL to 1, which is ring 3, could this code also be executed in ring 0? So this is the conforming bit. In our example, we don't really have to care. You could set it to 1, you could set it to 0, it really doesn't matter, because if you set it to 1, then the set of all privilege levels that it can execute it in is 0, 0, and then all the ones that are below, which don't exist. So you can only execute it in ring 0. And then if you set it not to 1, but if you set it to 0, then it means that you can only execute it in 0, 0. But those are the same sets, so it really doesn't matter in our case. So set it to 0, set it to 1, doesn't really matter for the code descriptor. For a data descriptor, it's your decision, just remember it when you're going to be debugging. Then you have the read-write bit. So this again changes depending on whether you're making a code or data descriptor. So for data descriptors, it's a writable bit, which means, okay, can you write to this data? And sure, why not? I mean, we often don't want our data to be read-only, so it's actually convenient and reasonable to set it to 1. So yes, sure, we can write to this data. If you're making something very static and you wanted to secure it, right, with a GD, you could set it to 0 to have just read-only data. Read permissions are always enabled if it comes to data descriptors, because data wouldn't make sense if you couldn't even read it. Then it's the readable bit if it comes to a code descriptor. So if you're making a code segment descriptor, then the question is, can you read from it? Because you can't write to it. In no case are you allowed to write to code. So this is always disabled, but there's this question of, can you read it? Like, you can obviously execute it, as the CPU can fetch, decode, and execute. But, you know, you just have a bunch of instructions. Can you read them? Can you, like, take a look at the output operand? You know, and this might be convenient at times. It's not really that much of an annoyance in any case, so why not? Let's set it to 1. If you want it to be 0, set it to 0. It's not going to have much consequences for a code descriptor. Yeah. So then we have our last bit, which is the access bit. Now this is pretty strange. In pretty much any manual, you will get told that this should be set to 0. And on many forums, of like hobby OSDevs and stuff, you will see that people saying that this should be set to 1 instead. So, what is the reason for this, and which one should you pick? Should you trust the forums or the hardware manuals? So, let's talk a little bit about what this bit even represents. So basically, the CPU, at first it hasn't accessed any of those segments, where it defines access as, interacting with that data, registering that as successful. Registering that as successful. That's pretty much it. And that it considers, okay, this segment can actually be properly accessed. And when it is finally properly accessed, what it does is it flips this bit to 1. And now the CPU knows that it shouldn't do any extra checks, that it shouldn't bother with anything. It can safely assume that this is accessible because it was accessed before. So this will be changed to a 1. So it actually doesn't matter that much, because you can set this to 0, and this is the quote-unquote proper way to do so, according to manuals. If you want to stick to those, go ahead and set it to a 0. The problem is that it can be a little bit slower, and the CPU will have to register accessing that. Sometimes it will falsely think that it hasn't accessed it. You might encounter some problems. So, for that reason, many people simply set it to 1, so that the CPU can assume that it can safely access this without any extra checks, so it knows that it was accessed before. We're actually kind of fooling it that it was accessed before. And feel free to set it to a 1. You only really have to set this to a 0 if you're debugging something, if especially related to the GDTR or GPS, then you might want to switch it to a 0, but otherwise it can be a 1. But again, it's your decision. Okay, so those are the access bits. We have a general idea of what we want to set them to. You could literally copy this. You could not. You could copy this, or you could decide that you want to change some bits. Entirely up to you. And 0, 1, just remember, depends on whether you're doing a code or data descriptor, because it's the executable bit. Okay. So now, flags. So the first flag is granularity. So this defines how the limit address should be treated. And this is what I said about, ensuring that we're not limited to 20-bit addressing. Because if you were to set the granularity bit to 0, it means that it would take the limit address like it usually does, in the sense that one address corresponds to 1 byte in memory. So we can access this many bytes. So this is 0. And if you do that, then that's sort of inconvenient, because you're going to be, you probably want to go with a 32-bit mode with this, and you're not going to be able to use 32-bit addressing. And again, what have you enabled the A20 line for? Definitely not for this. So if you set this to 0, it's going to take it as bytes. If you set the granularity bit to 1, it is going to interpret this as the amount of pages. And this is sort of a hackish, but not really, because it's also semi-official, way to extend this range to 32 bits. So it's going to interpret this as the standard page size, such as 4 kilobytes instead of bytes, which will allow you to increase the address range. So this is the granularity bit. highly recommend to set it to 1. Then the next bit is the size bit, and it's actually a collection of 2 bits. No, it's 1 bit. Yeah, it's 1 bit. So the size bit simply dictates: do you want to go into 16-bit protected mode and 32-bit protected, or 32-bit protected mode? And this is what I talked about previously. Protected mode isn't just the x86 32-bit mode. It is a protected mode that offers protection features, and you could as well run it in a 16-bit mode if you want to, right? So you can have 16-bit protected mode, in which case you would set this to a 0, and a 0 means I want a 16-bit protected mode. But you probably want a 32-bit protected mode. It's probably the very reason you're trying to enable protected mode, which is why the size bit is going to be 1. Then the next bit is the long mode bit. Long mode is the 64-bit mode of the CPU, as I've probably mentioned in an earlier lecture. And currently, this is not a GDT that we're going to use in long mode, because we're trying to get into protected mode first before we go into long mode. So the long mode bit is going to be 0. It would have to be 1 if this was strictly for long mode. And a little remark: when the long mode bit is flipped to 1, the size bit would have to be 0. A 1 here and a 1 here doesn't declare any legal mode. Then, I'm sorry, just to fill this format, to have this nibble, we simply have a reserved bit. That is always 0, and it always will be 0. And it doesn't represent anything. It doesn't represent any parameter whatsoever. It just there as a sort of padding. Okay, great. So now we have the access byte, 1001, whatever, 011. Again, you can modify it however you want. Then we have the flags, which in this case is 1100. That's probably going to be identical if you want to go into 32-bit protected mode. Again, this is going to be different if you want to go into 16-bit protected mode, or if you want to be limited to a 20-bit address range. I don't judge. So we have our base address, we have our limit address, the access permissions, and the flags. So now we have every single value that one has to specify in a segment descriptor. The only thing that is left is to actually place that in the proper format. So the proper format for a GDT segment descriptor is to first place 16-bit of the limit address, so this is 16-bit, then 24 bits of the base address, so this is 24-bit. Then the access byte, which is obviously 8 bits. Then the flags, which are 4-bit. Then the limit address, which is 4-bit as well. And then we specify the last 8 bits of the base address. So base address, which is 8-bit. So just like that, in this format, we have to place our 32-bit base address, because 24 plus 8 obviously makes 32. Our 20-bit limit address, our 8-bit access byte, and our flags. So we know what these things should be. Now we should simply place it in our program, and it should be fine. And we will have a valid segment descriptor. Yeah. So if you actually sum those, right, this is 2 bytes, this is 3 bytes, this is 1 byte. Flags in the limit address make 1 byte, and this is 1 byte, so that's 1 plus 1 plus 1, that's 3, plus 3, that's 6, plus 2, that is 8, which means that a segment descriptor is precisely 8 bytes, and this is why we need that one reserved bit. So it wouldn't be 7 bytes and 7 bits, because that would be strange. Okay, so now let's talk about a couple practical remarks. We have specified that DQ0 is literally our whole null descriptor, and after that, also you could make labels, right? So you could say like null descriptor, and like colon, and you know, make those labels. It's not necessary. You don't have to do that, but it's a design choice you might consider, so that it might be easier to deal with GDT later on. But what you really need is a DQ0 for the null descriptor, then to make a segment descriptor, and it doesn't matter. You can make a code descriptor first. You can make a data. You could make a data descriptor first. Doesn't matter, but you have to have both. And you're going to place it just right after the null descriptor. So this is 16-bit. So we're going to define a word, and you're simply going to define those 16 bits of the limit address, which is just going to be a bunch of Fs. You could write them in hexadecimal. Binary doesn't matter. Obviously, the number system is not going to matter. There's no standard assembly instruction in most assemblers to define a 24-bit value. So you'll most likely have to define a word and then a byte, just a bunch of zeros, right? Then for the access byte, you'll have to do a whole db, and you probably want to do it in binary, so that you have, like, you know, I don't remember, it was like 1, 1, 0, 0, segment type, so 1. If this was a code descriptor, then this would be 1, and the data then it would be 0. Let's say I would start with a code descriptor, but like direct conforming, so let's make that 0, let's make that 0, 1, whatever, just a random value, and then you would put a B as in binary. You could convert it to decimal or hexadecimal, put it like that, whatever. Just place it into the format as a byte. Then, since the flags and the limit address are both 4-bit, you're going to probably have to define both in a single define byte instruction. So one way to do this would just be to say 1100, and then the limit address is just going to be a bunch of ones, 1111. B. That's one way to define this entire whole thing. And then the base address, which is just a db, and then you can just place a 0 there. For clarity, you could place 0x 00, doesn't really matter. It's up to you. And yeah, you simply define the code descriptor like that, just values defined next to each other in memory after the null descriptor. Then you put the whole data descriptor. It should be really simple. And congrats, you've made the null descriptor, the code, and data descriptors. So then to do the GDTR. So the GDTR is very simple because it literally only specifies two things. I think the size is actually first. I wanted to do the offset, but so it's the size and the offset. Let me just yeah, so size is first, and then you have the offset. Okay. So size is a word, so it's 16-bit, right? And it's simply the amount of bytes, except you subtract 1, and the size of your GDT, not including the GDTR, by the way. And then the offset is a 32-bit value. Yes, 32-bit. A D word. DD, define double word, right? 32-bit memory address that that the GDT is placed at. So again, really simple. And the size, yeah, it's just the size of the GDT in bytes. Except you subtract 1, and the reason you subtract 1 is because it goes under this assumption that you're not going to give it an empty GDT, because it would be very stupid to just give an empty GDT, so it just assumes this cannot be the case, so it maps 0 to 1. So the indexing of the size actually starts from a 0. So if your GDT, let's take an example, the null descriptor, as I've said, 64 bits of zeros, so it's going to be 8 bytes. Then, as we've said, the code data descriptors both have 8 bytes each. So it's 8 plus 8 plus 8, that's just 24. And since indexing starts from 0 and not from 1, because 0 is mapped to 1, 1 is mapped to 2, and so on, then to put the size in the GDTR, you simply do define word, because it has to be 16-bit, and then you just put 23. If you have TSSs, if you have code and data descriptors for the user space and such, you'll have to modify it accordingly. Then the offset, we just do a DD, and then you place the address of your GDT. So you might know the address of your GDT. For example, you might know that, hey, this is 7E00, because you might have put the GDT right after loading in more disk space. So this is something you might have done, and you might know this. Alternatively, this is also considered better practice, to actually define this null descriptor label, where you do the DQ0 before like the code descriptor label, where you put the code descriptor and data descriptor, right? And then you simply do DD null descriptor, because that way it's going to take this address, because a label is nothing more than just a memory address of a given instruction that you pointed to. And you simply do that, and it's obviously going to give you the offset, which is the starting address of the GDT. The reason it's called the offset is obviously when you move through these bytes and you index them, you would have to offset, for example, 1 or 2 by this address to get the address of that byte in the GDT. I think that makes sense. So this is the GDTR. Very simple. And this is the whole GDT. Also, theoretically, the GDTR is not a component of the GDT, but come on, they're like very, very strictly linked. Okay. So, now how can we actually, okay, so we've placed a bunch of bytes and words and everything in our program, but those are just, definitions, and we're just placing zeros and ones into memory. How does this actually work? How can we make this GDT function? Well, the x86 CPU will literally do all of that for you. So this is very convenient. The only thing that you have to give it is the dereferenced address of your GDTR. And it literally has an LGDT instruction, which is load global descriptor table, not to be confused with LGBT. So this is the load global descriptor table instruction. Just place the dereferenced GDTR address, and it's going to load that for you. Yeah. So it takes so what it really does is it takes the insides of the GDTR, but I'm usually just define it as a separate thing, as I've said, with GDTR, and then you can just point to a dereferenced address of where you place the GDTR, and this is usually how it's done. So you just load the global descriptor table from the dereference address of the GDTR, and you could just define the label GDTR before placing your, DW23 and DD with the offset. It could be the null descriptor or something. Yeah. And you just perform this instruction, and the x86 CPU will literally load the whole GDT for you. And this is actually pretty much the hardest part if it comes to getting into protected mode. So it's going to be very easy from now on. So one more thing that you theoretically don't have to, but really should do before going into a higher bit mode is disable interrupts. So there are two assembly instructions in x86, STI and CLI. So this one stands for, so basically the x86 CPU has something called the interrupt flag, which simply dictates, okay, are interrupts enabled? So the clear interrupt, so this is clear interrupt flag, and what it does is it sets that flag to 0, and this is the set interrupt flag instruction, which is going to set that flag to 1. So STI, it enables interrupts in a sense, and CLI disables interrupts. So before going into a higher bit mode, you probably want to perform the CLI instruction, and that is because if an interrupt were to occur, as you might remember, by default, the programmable interrupt controller that is found on most x86 CPUs, which is the 8259, it redirects those interrupts to the BIOS. And the BIOS can give 16-bit instruction code, which in a higher bit mode is going to be gibberish. And this is one important thing to remember. You will not be able to use BIOS instructions and any help from the BIOS once you go into, for example, 32-bit protected mode, because the instructions you would get are 16-bit and they would be gibberish. You could use them in a sub-mode of protected mode, which is called virtual 8086 mode, but that is beyond the point. So you probably want to do a CLI just to secure yourself. So this is highly recommended. So perform a CLI at any point. You could do it before loading the GDT, after loading the GDT, before turning on and enabling the A20 line, after enabling the A20 line, doesn't matter. But you want to probably disable interrupts. Okay, so the last thing that remains is actually going into protected mode. And this is very simple. you simply have to flip, or, well, not flip, but ensure that, well, pretty much flip. Okay, so what you have to do is the control register 0, it's a register in the x86 architecture, and its youngest bit is the protected mode bit. And the moment that bit changes to 1, it is going to have the ability to execute 32-bit protected mode code with the setup that we have constructed. So, CR0 is simply not a register that is directly accessible to us, so we can't just or CR0 with 1 and call it a day. We cannot do that. We have to first move this to some intermediate register that we can perform operations on. Right now we could even use the extended A register, which is 32-bit. We are allowed to do that. So move EAX CR0. So you move the value of the control register 0, just so we store it, don't override anything. Except for obviously the protected mode bit. So we move this into the extended A register, then we OR the extended A register with 1, which is going to ensure, by the same logic that I used for FastA20, right, that this protected mode bit is flipped. Then we move the corrected value back to the control register 0. Congrats, you're now pretty much entirely in 32-bit protected mode. And I say almost because it's not safe to do 32-bit code yet. But you're pretty much in 32-bit protected mode right now, once you've done this. Okay, cool. Now, what do we actually do to execute 32-bit code? Well, first, as a practical remark, I would like to state that most assemblers, they'll by default, if you do a binary format and everything, will assemble to a 16-bit mode. If you're not doing it, then you should have figured out that you should place something like 16 bits at the top or whatever. Now, you also have to place a 32 bits tag or whatever you have in your assembler so that over here you know that the assembler knows to convert this to 32-bit instruction format. So you'll probably want, you'll have all your code over here that will go to protected mode, and then in the 32 bits you'll probably want to define a label so that it's easy to jump without manually determining the address. But manually determining the address could be difficult, so you could just define a label. You could call it something like main 32 or whatever, or PM for protected mode. It really doesn't matter, you just define a label, you place some code under that label, for example just an infinite jump, and perhaps I should write that like so. You just do an infinite loop like so, by jumping to the address of a jump instruction. And okay, how do you execute this 32-bit piece of code properly? Well, after you enabled 32-bit protected mode, you should do something that is colloquially sometimes called in the OSDev community a for jump. So the proper explanation for this is that we had our segment offset system, segment offset addressing. So now the offset is your address. Your offset is this huge thing that you can use for your addressing. Cool. This is where you will place your addresses. But the segment, it will now describe what segment should this be accessed as. And I'm talking about the segments that were described in our global descriptor table. For us, what we will want to do is we will want to jump to the address of our 32-bit instructions, and we want to execute them as code. We want the CPU to interpret this as code. So our segment has to be set to the amount of bytes after which the code segment descriptor begins in the GDT. So if you placed the code segment first, so you placed it right after the null descriptor, right? The null descriptor has 8 bytes, so the segment is going to be 8 if you've placed the code descriptor first. If you placed the code descriptor second, so after the data descriptor, this segment value will be 16 for this bar jump. And the offset will be the address, the actual address of where you'll want to jump to, which for us is just going to be our label that I titled PM. So after you do this trick with the control register 0, what you'll want to do is perform a jump instruction with the segment 8 or 16. I'll just do 8 for the sake of simplicity. Assume that the code segment is first. Described in the GDT, you just do 8:PM, and now with the proper new usage of the segment and offset, you can jump to this, and it's going to be interpreted as code. Great. So now this is the proper way to start executing 32-bit code. But there's one more thing to ensure. We want, so there are different registers which are used for some instructions when we talk about the segment of an address. So for example, in the previous lecture, I probably talked about the ES register that is often paired with the DI register to create a segment offset structure. So often this ES register is going to be used for specifying the segment. And now many operations that we'll perform will check for the segment in those different segment registers, such as ES, the descriptors, not the descriptor, the register that could be used to store the segment. And since it's going to be reading data, what we want to do is set all those registers, just in case, to what is our data descriptor. So that with this new usage of our segment offset structure, when it tries to read an address which is stored in the offset, the segment is going to be the position of our data segment descriptor in the GDT, so it's going to read it properly. So sadly, the segment registers are not registers that we can access directly, so we also have to use an intermediate register. And all of them are 16-bit, by the way, because segments are 16-bit. That's it. So it makes sense for segment registers to be 16-bit registers. So over here, before you execute any code, such as the jump instruction, what you're going to have to do is set those segment registers. So first, load the position of your data segment descriptor into some intermediate register. The intermediate register should also be 16-bit. I arbitrarily picked this 16-bit register, which is AX, but you could use BX, you could use CX, it really doesn't matter. So, I'm going to set this to 16. I'm going to assume that the data segment descriptor is put second, so after the code descriptor. If it's the reverse situation, then this is going to be 8. And there are 5 segment registers where we have to set. DS could be used. ES could be used, the one that I actually mentioned. FS, GS, and SS. So DS, ES, FS, GS, and SS are 5 segment registers that could be used for referencing the segment, and so that we ensure that it reads it properly as data, we're going to set them with a new interpretation of the segment offset to the position of our data segment descriptor. And after we've done all of that, we can say that we can now properly execute 32-bit instruction code in protected mode. And now you can do a jump, and now you can say that you're actually executing something in a 32-bit mode, in fact in a 32-bit protected mode. So, a couple of remarks. Right, you can't use BIOS instructions anymore. This is very important to remember. If you want to display a value now, you can't do it with the help of a BIOS. So you have to know what VGA mode you're in, you have to know what buffer does it use, and then you can, for example, write values to this buffer to display characters on the screen. This isn't actually that difficult. But again, if you want to read from the disk, write an ATA or a SATA or an NVMe driver. That's what you have to do now, right? Or implement reading from a USB mass storage, whatever. You're not going to be getting the help of the BIOS for that. So, that is pretty much everything that I wanted to cover. So I hope that this transition to 32-bit protected mode is a bit more clear now. And in the next lecture, I plan to go into long mode. And in order to go into long mode on x86, you have to enable paging, which is a topic that is quite difficult for a lot of people. And I would like to put a lot of effort into that video. It's probably going to be a very long video. I really want to talk about some details about enabling x86 paging, not managing the paging yet, but I'll probably talk about that in the kernel. But this is pretty important of the lecture, because it is the last lecture where I'll talk about actually setting up an environment for the kernel. And then I'll actually start talking about the kernel, and that'll be some interesting stuff. So yeah, I think that is indeed pretty nice. And I hope that the video about paging will go well, and then another video about loading the kernel. I'll probably talk about some. I'll probably make one additional lecture at some point where I talk about more bootloader considerations that are a bit more, well, perhaps not advanced, but that one might features that one might notice that are missing if someone wrote their own bootloader instead of using a bootloader already made for them. Which is why it is usually recommended to really just use a bootloader already made for you. Anyway, that is everything I wanted to talk about in this lecture. I hope that this was clear. If you have any questions, leave it down in the comments. Generally, leave comments. I like knowing that someone even watches those. So, thank you very much for listening, and I hope that you'll watch the next lecture.